High dynamic range is basically about real-world lighting. So in the real world, you have lighting which ranges from starlight all the way up to bright sunshine. Maybe not in this country. And the problem is with real-world lighting, up to now, camera technology simply hasn't been able to capture without, for example, the use of additional lighting. And HDR, high dynamic range, allows us for the first time to actually capture this data with camera technology, such as the one we have here. We can then manipulate it in post-production and then display it on special high dynamic range displays, and for the first time you can actually see the full range of real-world lighting on your laptop or on your television. Basically with high dynamic range, if the human eye can see it, the camera can capture it, and that's the difference. Whereas before with traditional camera technology, you haven't been able to capture what the eye can see. You either have under or overexposed parts of a scene. At WMG we have a unique HDR pipeline, all the way from capture, manipulate to display. So the first thing we have to do is capture the data. We need these revolutionary cameras which can capture 20 f-stops of lighting at 30 frames a second at full HD or high definition resolution. That then is compressed onto a device such as this, which allows us to then actually manage it. We can then move it into some sort of post-production or for use in dynamic image-based lighting. And then from there we can transfer it into these new HDR displays, which allow you then to see the real-world lighting. Basically we've been doing high dynamic range research for a number of years. And we had the opportunity to build this camera. I think without this is the camera that has really made the step change, because as I say, we can do research, but until you've got actually something to try it on and actually the technology to try it out, and you can't really validate and verify your results. And I think that's the crucial thing. This camera is giving us the opportunity now to actually show that we can capture it, the first time we've been able to do this.
So we see here a comparison between a professional broadcast video camera and the high dynamic range video camera. In these extreme lighting conditions, the normal broadcast camera is coping quite well until the person being interviewed starts to move, and then you realize that the light is actually affecting, has a major impact on what you're able to see at any point in time. Whereas with the high dynamic range video camera, because we're capturing all the exposures, we're able to compensate for that and produce an image which is a far enhanced viewing experience. This is not a product, but it's a prototype. We're able to get all the information. There are some issues technical issues which we're addressing, but that's the nature of research. But it really, in terms of the ability to capture something spontaneously, you don't need the lighting crew to come up to capture it. If you see something you want to film, you can just film it. You don't have to worry about the need for extra lighting. The problem with these cameras is that there's a price to be paid for capturing the real-world lighting, and that's basically the amount of data. So the amount of data we're getting is 24 megabytes a frame. That means you've got 42 gigabytes for a minute of footage. So if you imagine your standard USB stick can hold 8 gigabytes, you need 5 of these just to hold a minute of footage. And so what we've been doing at WMG is working on compression technology which allows us to make this manageable. So you can actually move data around, move this HDR data around on existing infrastructure, which you can't do without this compression. So once you've got the compressed footage, you can then take it into a manipulation package, for example, image-based lighting, we'll see just now, for post-production, adding in computer graphic imagery, etc.
So image-based lighting is a rendering technique. Rendering is the process of simulating lighting using software packages. So image-based lighting gives us the ability of, once we've captured the high dynamic range lighting with the camera such as the one next to me, we can then put it in a piece of software such as a renderer and use that lighting to light virtual objects as if they were in the environment in which the original light was captured. So this is a demonstration of a dynamic image-based lighting that we've prepared earlier. It shows a virtual car which was done in software being rendered with lighting captured from the camera. The lighting is placed all around the object, as such the object is within the sphere of the lighting. We can see the false color of the lighting, which shows the different luminances which cannot actually be displayed on this monitor. Also, we can see different exposures which highlight different aspects of the lighting. The lighting can be done dynamically. As you can see, the camera can move, any object can move, and the camera allows us to light the virtual object from any angle. So this camera gives us the ability of doing things much faster. As I said before, the original cameras, the static cameras, would take between 5 to 10 minutes. Now we're doing 24 frames per second. So this gives us incredible opportunities of doing things we couldn't do before, like having moving clouds, showing off explosions, and lots of dynamic environments. It's cutting-edge technology. It's the only camera of its type in the world, and it gives us the opportunity of doing certain things that no one else can do.
So this is the final stage of the pipeline. This is the HDR displays. And what we have on over there is a standard LCD, top-of-the-range LCD monitor. And behind me here, we have a high dynamic range monitor. And the difference between the two is that a high dynamic range monitor is not just an LCD panel, but behind it is an LED panel. and it's a projection of the LED panels through the LCD, which is giving you this extra information, extra lighting. On the LCD, you get a lot of information, but you still lose information, particularly in the clouds. And you can see here, we have all the information captured, the real world lighting, which your eye would see, whereas on the LCD version, you simply can't get that. And what we're actually showing on the LCD version is not a single exposure, but it's the HDR content is compressed in such a way we get the best possible quality. But even so, we still can't give you everything that you need to see the real world.
I mean, the question is who would use it? And the answer seems to be certainly television companies, certainly Hollywood. And one thing we're exploring is see whether this idea of capturing full extreme of light within a certain circumstances is of value to people undertaking training to be surgeons. So capture the light in operation. So you'll be able to see not only where the light is shining on a particular part of the body being operated on, but what's going on around you. A fourth arguable application is in terms of creating better simulators for security and for training and for understanding. Potentially the market is very, very big.
I think we have a unique opportunity, a world-first opportunity in WMG to do this. We have, the top of the range, probably the best camera in the world to do this with. So I'm very excited about the possibilities that how we can take this research forward because we've got access to this technology.